So let's see if we can better balance between the bias and variance, the high bias in the TD learning approach versus the high variance of the Monte Carlo approach. So a simple way to do that, and later on we'll learn probably a bit more sophisticated ways, but a simple way to do it is to do what's called n-step TD learning. So for TD learning that we've seen so far, we look one step at our immediate step neighbors, right, for each state, and we propagate the Q values from that step. However, technically we can do two-step look-aheads and look at all of the neighbors that are two steps away and propagate the values from there, right, and so on. And then we'll have some kind of a combination of the observed rewards, right, that are at the end of the day unbiased. They do come from the real environment, but we're starting to introduce more and more variance because the probability of sampling a specific set of rewards, a specific trajectory, diminishes, and usually diminishes exponentially. So this is the idea behind n-step TD learning, some continuum between the Monte Carlo extreme and the TD learning extreme. It is n-step TD learning. Once you go away from a single step, we do two steps or so on, then we'll have to assume a specific policy that we are following. And now n-step TD learning becomes an on-policy algorithm, right? As long as the n is greater than 1. At 1 we have Q learning, as we've seen before, which is off policy. But if it's greater, then we have an on-policy algorithm. And as long as n is bigger, we're more and more sensitive to the policy that we're using. It does perform, n-step TD learning performs local learning. We're propagating values from neighbors, so it does perform bootstrapping. But, as I said before, with further and further neighbors, so we can define how far the neighbors are. And we are still trying to perform some efficient value propagation, so rely more on a Monte Carlo value propagation, where we can propagate values along a longer trajectory while still avoiding the high reliance on a specifically sampled trajectory. We would like to actually balance, as I said before, between the variance and the bias. So what does that mean? So let's assume that we sample a specific episode, right? And we do that also for one-step TD learning, but also for Monte Carlo approaches. It's just that they perform the updates, the Q updates, in a different way, but you can view each of them as sampling an episode, trajectory in the environment. So the question is, and this is where the different algorithms differ, how should, let's say, the Q value for state S0 and action A0, the Q value for this, for S0, A0, how should it be updated? So, as before, we perform TD learning, right, in the most general case, where we set the new Q value to be the old Q value, plus some alpha learning rate, and then the TD error, the temporal difference error between the new value that we just sampled and our previous estimation, the current estimation of the Q value for S0, A0. Okay? And what I'm claiming is that the different algorithms only differ at how they compute the new value to be assigned to S0, A0. Okay? If we do one-step TD learning, well, we're saying that the new value is simply the immediate reward that we observed at time step, after time step 0, plus a discounted sum of future reward represented as the Q value at S1, A1. Monte Carlo approaches have a different way to define the new value. In Monte Carlo approaches, we do not rely on the estimation, we don't do bootstrapping at all, but we simply sum all of the rewards that we've seen in the trajectory after visiting S0, A0. Right? So this is why it's very high variance. So Monte Carlo says, no, I don't want to use any estimations in the next stage. I'm just relying on the actual rewards that I see. This is very sensitive to the transition that we sample, but it is unbiased, it is correct. These are the true rewards that we've seen in the environment. But as we said previously, this is not always what we want to do. This is very high variance sample. So n-step, the n-step TD learning exactly allows us to play between, or to define the continuum between the full Monte Carlo on the one hand and the one-step TD learning on the other. Okay? How do we do that? So we choose some n, let's say it can be 2 steps, 3 steps, or whatever. We sum all of the rewards until that n, and at that n, then we rely on the approximated value from that point onwards. And now we can play. If we can play with this n value, of course, right? If we have a very bad estimation, we might want to rely more on the actual observed reward and push the q value further to the back, where gamma times to the power of n will be so low it won't really, the q estimation error won't be that impactful. Else, if we have a highly noisy environment and fairly good estimations, then we want to keep a small n, right? However, the important thing to see is that n-step TD learning is actually a generalization of both Monte Carlo learning and one-step TD learning, right? So one-step TD learning is what we've seen before. This is also known as TD0. Why? I'll explain why. For now, don't worry too much. Why is it also known as TD0? It's more commonly it's known as TD0, and I'll explain why later on. We learn a different algorithm, a different generalization of TD learning that explain why this is also referred to as TD0. At the other extreme, if we set n to infinity, we have exactly the Monte Carlo algorithm, right? Which is sum all of the rewards until the end of the episode. And now you can see that n-step bootstrapping, 2 steps, 3 steps, and so on, is anywhere in the middle, right? We can define any variant that is between Monte Carlo, the full Monte Carlo approach, and one-step TD learning. Okay, so let's see how this will work in practice. So let's say that we have a very simple grid environment. Let's say that in this example, let's say that there's no noise. That is, you're trying to go somewhere and you'll get to that cell. And you can see that we have some starting location and some go location, that once we arrive to that go location, we get some high reward. And let's assume that we have some discount factor that is smaller than 1. And then at the beginning of training, of course, okay, so our goal is to learn a policy that will get us to the goal as soon as possible. Of course, this is something like this, go right, until you get to the goal. But we have to find this policy through samples in the environment, right? So through trial and error, through reinforcement learning. And so initially, we sampled the trajectory that we see here on the left. Okay, it's a bit of a long trajectory, but eventually we go to the goal. Now, we can propagate values back to our environment, and eventually we will be able to converge on the optimal policy, right? Through Q-learning, through Monte Carlo approaches, or any other approach that we've seen previously. And now the question is, let's say that we would like to apply n-step TD learning in this environment, and my question would be, what is a reasonable n for this scenario? Okay, so we can do, let's say, one-step SARSA, one-step TD learning. And we can also, for instance, propagate the values back in 10-step TD learning. Can you think of the benefits and drawbacks? So what might be inefficient in performing one-step TD learning?
Slow value propagation?
Right. So we'll do our first episode. We'll only be able to update the value here. Right? We'll say, oh, this is a good state. We're one step away from the goal. But then we're losing a lot of, well, potentially beneficial samples. What's the problem with, let's say, propagating value through 10 time steps?
It's giving high values to actions which are not good.
No, we have quite high variance, right? So this state here, for instance, you can see that it is 1, 2, 3, 4 steps away from the goal. However, the value that you're going to assign it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be the goal reward discounted 10 times. So very high variance. I mean, you'll be there at a different time and you sample a different trajectory, it will give you a completely different value, right? This is the balance that we discussed previously that we'd like to perform. So again, I would ask, what would be a reasonable n here?
Maybe 6.
6. 1, 2, 3, 4, 5, 6. No, I would say 6 is still very bad. 6 will give you a bad estimation. You can go to the goal in 2 steps, but the trajectory that you sampled does it in 6. It's kind of a bad value to place at the 6 steps away from the goal.
Maybe 4?
4 or maybe 3 even, right? You can see the 3 here. Yeah, that's actually a correct estimation, right? You're 3 steps away from the goal, and yeah, that's true. And at each location here, you're kind of, you can see that you're kind of changing your direction every 3 steps. So I would say 3 would probably be a good value. But as we said previously, 1 step is very low variance, but inefficient learning. We have very slow value propagation if we do it in 1 step. 3 steps looks good. 10 steps might be might be too high variance. Okay, but you can see that just by eyeballing this example, we see that actually probably the best n-step TD learning is not 1 and not the full Monte Carlo. Full Monte Carlo, you can see, is very noisy, a very noisy trajectory that we chose here. While 1-step TD learning will be very slow in propagating value. But 3 steps seems kind of consistent here, right? Every 3 steps it's changing its direction above. And again, this is where we try to strike a balance between learning speed and value variance, and wrong values, right? So this leads us to the following pseudocode that is a bit long, I know, but there's a lot of bookkeeping that we need to keep when we perform n-step learning. When we perform n-step learning, of course, at each time step we have to go back n-step in the past, compute the value and propagate that forward. So there's some bookkeeping. It's not too bad. I mean, the pseudocode looks a bit long, but it's mainly about remember this value, remember that value, propagate that, and so on. If you just follow this pseudocode, it should be fairly simple to implement. You want to do a running example? Let's do a running example. So we'll again ask Vav to help us with the running example, and I'll try to give some pointers.
Alright. Hi everyone. So in this example, we have our domain on the bottom left. An arbitrarily initialized Q function, and we have our table here of what an episode will look like, starting from state S0 going up to state S2.
No, that's so the table. So you have the Q value table on the left, and there the table standing up. So this is dependent on the n value that you select. Right? So we're doing n-step SARSA. In this example, what n are we choosing?
2.
Right, n2. So this is why we have 2 SARSAs, S-A-R-S-A, R-S-A, Okay, so we have two SARSAs in order to, well, remember everything. Okay.
So, just like TD learning, we're going to sample a few episodes and then go through the time steps for each of the episodes. So for the episode 1, starting at state S0, we select an action write and store it in a table. And then for each state, starting from the last state that we visited, we take actions and keep so we actually do the back propagating in the end. So right now we're just collecting this episode. We take an action, see a reward until we reach either n equal to 2 or the terminal state. So in this case we keep sampling until we exit. So in this case we've exited, so and we have n equal to
So
2 states.
we don't perform a full episode, right? So we have 40, right? The time step, it's just a continual learning. But we select off the actions and let's say sample. We don't sample a full trajectory at the beginning. We sample sufficient state and actions to fill out our n step learning, right? So if our n is 2, we perform 2 time steps in the environment and then we start learning. But we don't. It's not episodic learning. We don't have to complete the episode. We do 2 steps, and now once we saw sufficient time steps in order to perform our learning, we're starting to perform our learning, and we'll do this for each step onwards. Okay.
So right now this is the time step for like Dr. Sharon said, we've sampled an episode. We've collected.
No, we didn't sample an
sorry,
episode.
we've sampled
2 steps.
2 steps, as you've said, n equal to 2,
Right.
and that's sufficient for us to now update our Q values using these 2 steps. So at this here T would be equal to let's say 1. I mean 2. I mean, what is T here?
Tau is the time whose estimate is being updated. Okay, so we'll start by estimating our first time step. This is the first update that we do. We update time step 0. So we perform two time steps. Now we go back in time and say, okay, now I'm ready to update time step 0.
So here our tau would be 0 minus 2 plus 1, which is minus 1. So
No. Our tau. So now we already performed. So T is now 2, right? We performed 2 time steps. And now we're ready to do the update. Okay?
So we.
So tau is 0 now.
Yes.
Okay, we performed 2 time steps. Now we're ready to update
Okay,
our.
so T
initial
here
time
is
step.
2.
T. So we already performed. Actually, we performed the 2 time steps, right? We performed the 2 time steps, and then we are now at time step 3, and now we're starting to update. So we finished 2 time steps. We're ready to start updating our Q values.
All right.
2 time steps ago
So-
at the beginning, right? At T0.
So if we've taken 2 time steps, that should give us a value of tau greater than equal to 0, and which we then enter this Q update condition. We see that.
So we accumulated capital G. We accumulate all of the rewards
Yes.
up to our n, which is 2, right? And then we do the Q update based on the n step return, that's in capital G, minus the Q estimation at the next.
State.
Sorry. So G also includes capital G also includes the Q estimation in after time step 2, right? At the next state that will.
Yeah. So it is the approximated Q value for the current step
Right.
calculated looking n steps ahead instead of
Right.
just one step
This is
ahead.
the new value.
Yes.
Capital G is our full estimation of the full return
Yes.
moving forward. Right. And minus Q, which is our current estimation. This is the TD error. Right? Okay.
So the final condition is if pi is being learned, then ensure that pi is greedy with respect to Q. Okay, that's
Right. This is for, okay, so it's for, you can either use this to estimate a specific policy or to control, to update a policy. In some situations, we are interested in evaluating a specific policy, but here let's assume that you're also updating the policy, right? So it just tells you here, just be sure to update your policy correctly based on the Q value.
So we've updated our Q function, we've updated our policy based on the first two samples that we've collected. We now move on to collect another sample.
Another one-time step.
Because we have two time steps, now we collect one more. So now we have three. That's sufficient to make a two-step update. Since it's more than two, more than one, sorry. So now we have three samples totally, and in this case it is the terminal state, so we have to exit anyway.
We don't exit. Even once we saw the terminal state, we have to go back in time and update
Okay.
what we've seen previously, right?
Yes. So we either so reach the terminal state or not. If we have sufficient number of samples given n, we perform an update.
Right.
Yes. So now our tau would be again 1. 3 minus 2.
On the left, right?
3 minus 2 plus 1. Sorry, 2 minus 2 plus 1, I guess. So tau will be 1, and we calculate g again, which in this case is going to be 9. We are seeing right now we're in state what state? Y?
Right, Y. So we updated X already, now
Yes.
we're doing Y.
So in Y we have a gamma of 0.9, and we take action right, going to state Z, getting a reward of 10. So back propagating that, we get a value of 9 at state Y action right. We use that to update our Q function and our policy, and we then move forward to collect the next time step.
But we terminate.
But in this case, we've reached the end of the episode, so we terminate. And
we still do the updates.
We still check if tau is greater than 0, and if it is, we perform an update again. And this is right now for the last state, for state Z.
Right, but this is very important actually, right? For state Z, you might say, well, I can't do two-step look ahead because it's terminal state, right? There's nothing beyond that.
Yes.
But we still need to somehow learn values there, right? So it's still important to do the updates, even if for the terminal states once, or those close to the terminal state, even if we don't have the full n look ahead, right? In this case, because we cannot. But else we won't be able to ever update.
Yes, because nothing would propagate.
Right.
Yes. So right now we're updating the terminal states Q values and the policy. And so we've completed an episode and got some new Q values for each of the states. We repeat a new episode. We again start at state X.
And so on.
Yeah, and so on. We repeat it again.
Okay, thank you.
And get converted.
Thank you.